So, we have been looking at the piston in a baffle problem, and we started off with the Rayleigh integral, and we have specialized the Rayleigh integral for the piston case, and after simplifications we have arrived at this situation here. Okay. So, now we look at the d phi integral first. So, if I have from handbooks, okay, from handbooks, if I have 1 by pi integral 0 to pi cos of x cos phi 0 d phi 0, okay, then that is the cylindrical Bessel function of order 0 of the first kind. Okay. So, here we have 0 to pi, okay, we do not have pi in the manner we will want. So, we will bring pi up over here. Then we have a cosine cos phi 0 cosine d phi 0 of x. So, the result of that will be the Bessel function 0 of k r 0 sin theta into pi. Okay. So, let me take this to the next page. So, we have this thing over here. So, this can go and this can go. So, now this term, let me write it first, is equal to j omega rho u n equal to j omega rho u n okay, e to the power of minus j k r by pi r integral 0 to a into j 0 k r 0 sin theta into pi r 0 dr 0. So, this pi now can go. Okay. So, we have reached one stage. Now, another identity 0 to a Bessel function cylindrical first kind order 0 gamma r into r dr is equal to a cylindrical Bessel function order 1 first kind a gamma over gamma. Okay. So, here gamma is k sin theta, k sin theta. So, what we have now is a j1 k a sin theta by k sin theta. Okay. So, what is the result now? J omega rho u n e to the power of minus j k r over r into a j 1 of Ka sin theta by K sin theta. We will make it Ka sin theta and a square. Okay. Now the volume velocity of the piston is area into velocity, normal velocity, that is called Q. Okay. So therefore a square into un will be Q by pi. So this is equal to j omega rho Q by pi r e to the power of minus j k r j1 of Ka sin theta by Ka sin theta. Okay. So now a slight digression here, just if Ka is made very small, it's a non-dimensional number, it is called the Helmholtz number. We have seen that it helps us go to the monopole approximation. Okay. So if we do that, what do we get? We get pressure at a certain r comma theta is given by j omega rho Q by pi r e to the power of minus j k r, and for small arguments, so for small arguments x much smaller than 1, j1 of x approximately becomes equal to x by 2. So if we now use that, this becomes Ka sin theta by 2 and we have Ka sin theta, then this goes with that and I get j omega rho Q by twice pi r e to the power of minus j k r, which is twice the pressure due to a monopole. So this is like monopole, this is like monopole placed in a baffle. The pressure that would have gone behind, okay, in free space gets reflected because there is now a baffle, it is now sitting in a baffle, okay, and therefore the pressure here doubles. Okay, pressure there doubles. So that's just to show you that a monopole in a baffle does what, okay, but this is our expression we have to deal with. Okay. So that, let me just write it here. Let me just write it here. Okay, that is the expression. Okay. So now how does this look like? Okay, how does this? So let me just okay, before I move further on, this is a monopole sitting on a baffle, and notice that it is independent of theta, independent of theta. Okay, so it has uniform radiation in all directions. Okay, so there is this monopole sitting on a baffle, it has no theta dependence, of course has no phi dependence also. Okay, so now this is the expression we have. Now how does this thing behave? I will have to take it on to the next page again, so let us take it. Okay. Now if you recall the geometry, we have this, we have only half the space available, upper half x, y and z, theta goes from 0 to pi by 2, 0 to pi by 2. Okay. Okay. Now as theta goes to 0, we showed that as this argument goes to 0, this acquires a value x by 2, we have shown that, right. Now the maximum value of sin theta is 1 and it undergoes no more zeros. Okay. So if Ka is a small value, K is a small value, let us say 0.01, then Ka sin theta starts at 0 and moves to 0.01. As theta goes from 0 to pi by 2. Whereas if Ka happens to be, let us say 1000, then Ka sin theta goes from 0 at theta equal to 0 to 1000 at theta equal to 0. Okay. Now the J1 function is an oscillatory function, it is an oscillatory function. Okay. So now what happens, oscillatory and decaying of course. Okay. Now what happens? And this is happening as a function of Ka sin theta. Okay. So if Ka is very small, okay, if Ka, so this is J1, okay, as a function of, this is J1 value as a function of Ka sin theta. So as for small values of Ka, the total argument change is very small as theta moves from 0 to theta equal to pi by 2. So as a result we may see only this much, okay, K sin theta maximum value may be only here. Whereas if Ka is much bigger, if Ka starts to become bigger and bigger, then the Ka sin theta, as theta changes, goes through much more values and reaches a bigger value. Okay. As a result, what will happen is that the J1 term, okay, will go through maximas and 0 values and so forth. Okay. So what will happen now is that if we look at the sound field, that being the z axis, if we look at the sound field and we move at a constant radius, at a constant r, okay, it's a constant r, we move in the theta direction, suppose, okay, and if Ka is very small, then the sound field will be more or less uniform with theta. With respect to theta, the sound field will be more or less uniform. Okay. Whereas if Ka becomes large, okay, then what you will see is a central big lobe, and then at some theta it will take a dip and go to 0. And then as you move further away, it will go to another maxima with a slightly lower value, and then at some other theta it will go through a dip, go through 0, and again at some other value it will acquire a value, maximum value, and then go and so forth. Okay. So if I look at it from the top, I will see a central lobe, I will see the next lobe, I will see, so it looks like kind of a flower. Okay, this is a peak, this is the peak, this is the peak, these are the zeros. Okay, and as Ka is raised further and further, this becomes narrower, the central peak will become narrower, and more of these side lobes will be accommodated. That is the nature of this solution. Okay, that is the nature of this solution. So that is the behavior with respect to angle, theta. Okay, we will see why this happens, we will see why this behavior happens. Okay. Now we will look at what happens on axis. Okay, on axis what happens? On the axis, okay, if we look at this piston like this, sorry, We look at this piston like this. That is my z axis right along the center, x and y. Okay. So, if I look at a point somewhere here, okay, let us say this point is r0 away and this point is z, this point is z away. Okay. So, what is my integral p r comma theta, okay, was given by, let me just see. Okay. So, now if we specialize this to on axis pressure, we get j omega rho Vn or Un, does not matter. Okay. Then for the pressure on this, I have R0 dr0 d phi 0 integral 0 to a integral 0 to twice pi, okay. Then this distance is e to the power minus jk r, which is square root of r0 square plus z square divided by square root of r0 square plus z square. Okay, divided by twice pi. Okay, this is the distance. If you want to, this is the distance, if you, this is the distance from a radiator point to a point on z. Okay. So, this is now theta equal to 0. Okay. So, this here is theta 0 point, this here is theta equal to 0 point. Okay. And what is r? R equal to z, r equal to z. Okay. And phi is anyway, it is symmetric with respect to phi. Okay. So, now what happens here? What happens here is that if we do the d phi integral, I will just get a twice pi because this expression is independent of phi. Okay. From any location r0, that distance is the same. So, it is independent of phi 0, and so what I get is j omega rho Vn by twice pi integral 0 to a, and d phi 0 gives me a twice pi. So, I get a twice pi e to the power of minus j k square root of r0 square plus z square divided by square root of r0 square plus z square. Okay. and then r0 dr0. Now if I differentiate d by dz of e to the power of minus j k square root of r0 square plus z square, I get e to the power of minus j k square root of r0 square plus z square, and derivative of this now which is equal to e to the power of minus j k square root of r0 square plus z square. Minus jk is a constant, minus jk 1 by 2 square root of r0 square plus z square into twice z. I am sorry, ddr0. d of dr0. Twice r0. Okay. So d e to the power of minus jk square root of r0 square plus z square, okay, is equal to e to the power of minus jk square root of r0 square plus z square minus jk r0 dr0 by square root of r0 square plus z square. Or if I bring this down here, I can bring this down here. One by minus jk. Okay. Now this is what we have over here. So this is an exact differential. Okay. So the result then is equal to j omega rho Vn by minus jk e to the power of minus jk square root of r0 square plus z square over 0 to a. So this is minus omega minus, okay, so is equal to minus rho CVN e to the power minus jk square root of a square plus z square minus e to the power of minus jkz. Okay. So now if we want to look at the magnitude of this, we want to look at the magnitude of this thing. Magnitude of this expression. That is our interest here. Okay. So this will take a little bit of time, okay. So I will close the lecture here, and we will continue this idea in the next class. Thank you.